Okay, hi and welcome to part 2 of Notes 3.5, Compound Inequalities. We left off in the last section of notes looking at how to solve compound inequalities, but we did that separately. This time we're going to take a look at what it looks like to solve them as one piece. So really the main difference, if we look at B here as our example, we can see it's a compound inequality. It's got a low part and a high part. We got two inequalities there. That's how we identify it. So with this, the way that we solve it is that whatever actions we take on the inside to solve for x, because that's our job, isolate that value there. In this case, it's only a move of this -3, which we're going to divide away. When we divide by this -3, we have to make sure that we do it to both sides. So that's how we can do it if we want to address it as a single compound inequality instead of separating it. Either way works. Either one's fine. Most people prefer this method where you keep it together because it's a little bit more efficient than separating it into two. And again, these are and inequalities. Okay, so let's go ahead and do this division, but there's one rule that we have to pay attention to, and that's one that's indicated right here, is that if we divide or multiply by a negative number, we have to flip our sign. So we're going to go ahead and divide that negative, but right now we're going to take a second to flip both of our inequalities. Okay, so now that we've done that, dividing by this -3, those cancel into 1, leaving just an x in the middle. 15 divided by -3 is a -5, and -6 divided by -3 is a +2. If you'll notice, our signs are flipped, so that's kind of different from the way that I've shown you the compound inequalities. And look, our low boundary is on the right side, and our upper boundary is on the left side. We should rearrange that. So let's go ahead and do that. I'm going to put my low boundary on the bottom. Make sure that you keep track of your inequalities. Those must also flip as you rewrite this. So now it looks like we're used to. We've got an x in the middle with less than signs on either side, and that's what we want to see. All right, so let's move down here to a word problem real quick. This is a traditional word problem that you would see with a compound inequality. If you read through this real quickly, it talks about a swimming pool, and then we've got a couple pH values, and we want to see if our pool is normal, as they would say, in the range that would be acceptable to swim. So if you pick out a couple quick pieces of information, we've got two values, a low value and an upper value, that say these are okay. If you're in between these values, you're good. They also nicely give us the word inclusive, which means that it's got an equal sign underneath. Okay, they go on to say that you've got two values already that you've taken, 7.4 and 7.9. What's the third possible value? They say, and they even give you the variable here, so they've made this extremely easy for us. So what's the third possible value? So we define our variable, check, and now we need to figure out what this average is for this to work between these boundaries. So let's write the average so we have an idea of what's going on. So 7.4 plus 7.9 plus our third reading of p. But an average isn't just the sum of those, it's the sum of those divided by however many there are. In this case, there's 3 of them. So now we're going to plug this into the middle of our boundaries as a compound inequality. So 7.2 is our low end. Start with our included less than sign. I'm going to write my average, 7.4 plus 7.9 plus my p, which I don't know my third reading, divided by 3. And I'm going to finish it with my included less than sign and my upper boundary, which is 7.8. So in this scenario, we're going to go ahead and continue on like we've done before, nothing new. We're going to isolate p, but to get to that p, we need to move, because there's an unshown set of parentheses there, we're going to move that 3. So I'm going to multiply everything by 3, both sides by 3. Again, this 3 and this 3 reduced to 1, leaving 7, well, actually, let me clean this up, because 7.4 plus 7.9 is 15.3, plus my p is less than or equal to, we'll put that in there. 7.8 times 3 is 23.4, and 3 times 7.2 is 21.6. The rest of the work is done for you, so you can follow along. What we find out, though, when we finish solving for p here, again, subtracting 15.3 from both sides, is that our last reading needs to be 6.3 or anything in between up to 8.1 for a pH level. If we fall for our third reading in between those two boundaries there, we find out that our pool will be considered normal. And again, it's a word problem, so make sure you write that out. All right, so let's talk about the other type of compound inequalities, one we haven't said too much about yet, which is the OR compound inequality. The OR ones, as you remember I hinted at, should have a graph that does not overlap, that does not intersect. So right here in the center was what we were used to with an AND inequality. But an OR inequality will not overlap. It's like the exclusion. It's like the opposite of the answers, if you will. So that's kind of the main difference visually and solution set-wise what a compound inequality is. Here's a note. Make sure that you do not write these as an actual together compound inequality. This kind of sounds a little funny, meaning that we can't write it like this with a value in between. They do have to be written separately and with an or, with the word or between them. So make sure that you're aware of that. That's what this note really means there. You should never have them as one. They should be two separate inequalities when you write them. So here's one example. You can pause and take a look at that if you want. Again, well, let's run through this one. I kind of skipped over it. There's my low boundary. There's my upper boundary. It says that it's greater than 7, so that means that it's not included. It says it's less than, not included, -3. So when I went to write this, I write my low boundary on the left. I write and it says that all real numbers are less than -3. So my solutions have to be less than, so I'm reading from left to right on this one, so be careful. That's why the sign looks like the greater sign, but if we read it from left to right, the solutions are less than -3. It says what it says here. And then this one says that their values are greater than 7, so my solutions are greater than 7. And what that looks like is this graph here. Okay, so now that you kind of have an idea of what they are, let's solve one. So here's a or compound inequality. It's two separate ones. We treat it just like we did before. So we're going to solve it like any other thing that we've solved. There's the x. We're going to isolate it. Reverse order of operations says subtract 7 from both sides of the inequality. Leaves a 2x for me. There's my inequality sign. -7 and +3 make a -4. And now we're dividing by -2. And I said dividing by a negative, so don't forget to flip your sign. So we're going to go ahead and flip that so we don't forget. These turn into 1, leaving an x on the left, and a -4 divided by -2. Two negatives make a positive, leaving 2. Or I could have the possible solutions of these. So I'm going to solve this one now. Add 4 to both sides. So I get 3x is greater than or equal to 9. Divide by 3, it's positive, so no sign flipping. Equals 9 divided by 3 is 3. So those are the two possible solution sets for this or compound inequality. So what does that look like? Here's my boundary. So I go ahead and it's not included, so I make a open circle at 2, and then it says my solutions are less than, to come to the point first, 2. So I go to 2, I find it, and I draw to the left because it says it's less than. Okay, so my solutions on this side, right, this is my upper boundary, my solutions on this side run into the greater than sign, so my solutions are greater than or equal to, so I make a solid point, greater than or equal to 3. So that means that I graph to the right. And that's the or compound inequality. So you do need to memorize that or compound inequalities do go away from each other. They do not overlap, they should not intersect. And compound inequalities should overlap, should look like a barbell, some version of included or not included. And that's it. I mean, that's the idea of the compound inequality. What are they great for? Intervals. We've already seen that. Solutions or solutions that are intervals. We know that inequalities represent a pile of solutions, not just 1 or 2 or 3. It's a whole solution set, as you will. So there's the notes for compound inequalities. If you have any questions, make sure you post them in class for me or in the community, and I will see you in class.